Welcome to this video. In this video we're going to talk about the parathyroid glands and vitamin D and the role of the parathyroid glands and vitamin D in maintaining blood calcium level. Okay, so all of the parts to this video will be placed in the playlist on endocrinology, so if you're struggling to find the successive portions of the video, I advise you to go to the playlist on endocrinology and you'll find them all in their correct order there. Okay, so let's begin this story by discussing the parathyroid glands. We'll come on to vitamin D much later. So the parathyroid glands, let's begin by discussing where they actually are. So you have 4 parathyroid glands, and as the name suggests, they are by the thyroid gland. So in fact, they actually are sitting behind the thyroid gland. So the first picture that I want to draw is a picture of the thyroid gland, and then I'll mark on this picture of the thyroid gland where the parathyroid glands would be positioned behind the thyroid gland. Okay, so let me draw a picture then of the thyroid gland. So the thyroid gland is in your neck, and it sits just in front of the thyroid cartilage, which is part of the larynx. So where your Adam's apple is, the fancy name for the Adam's apple is the laryngeal prominence, and that's a prominence of the thyroid cartilage. So that's the way you can find where your thyroid cartilage is. And just in front of that thyroid cartilage, you're going to have the actual thyroid gland, and that's what I'm about to draw. So the thyroid gland is symmetrical, and it has 2 lobes, a right lobe and a left lobe. Okay, so I'll try and get this as symmetrical as possible, and the right and left lobes are going to be connected by a small, narrow connection known as the isthmus of the thyroid. So here I'll try and get it as symmetrical as possible. Here is the left lobe of the thyroid. Okay, so here we have the right lobe of the thyroid. Remember, we are looking from the anterior aspect, and we're always giving right and left as far as the person who we're looking at is concerned. Okay, so we're thinking about this is their right lobe of the thyroid, their right and left. Okay, so this is the right lobe of the thyroid, and this one here then is the left lobe of the thyroid. And this connection between the 2 lobes of the thyroid gland is then called the isthmus of the thyroid, or the thyroid isthmus. Okay, isthmus just means a narrowing. Okay, so when people talk about the isthmus of a bone, that's the narrow shaft of the bone. So if you were, for instance, looking at the humerus or the femur, you know that on the 2 distal portions, the 2 distal ends, it gets thicker, and then in the middle it's thinner, and that's known as the isthmus of the bone. So it just means a narrowing. Okay, so isthmus, right lobe, and left lobe, and those are the basic features of the thyroid gland. So now let's actually talk about where the parathyroid glands would be. Now remember, I'm saying we're looking from the front, so we wouldn't be able to see the parathyroid glands because the parathyroid glands would be behind the thyroid gland. But what I will do anyway, despite this, is mark them on where they would actually be on this picture. So, if the thyroid gland was see-through, then we'd be able to see the parathyroid glands behind it, and you'd have 4 in total, 2 on each side. So you'd have 2 on the right side and 2 on the left side, and on each side you have 1 superiorly and 1 inferiorly. So they're at around these sort of positions. So here are the 2 on the right side, a superior one and an inferior one, and here are the 2 on the left side, a superior one and an inferior one. Okay, so I'll colour these in orange. These are the things that we are studying, these parathyroid glands positioned behind the right and left lobes of the thyroid gland. Okay, right. So now, just before we actually discuss the histology, let's give a brief overview of what the role of the parathyroid glands actually is. So the parathyroid glands, their job is responding to blood calcium level going too low. Now we'll be discussing blood calcium level in a bit more detail in just a moment, but for now understand that you have calcium ions in your blood. Calcium is a very, very important ion in biology. Okay, and you have calcium ions in your blood. Now, calcium ion level or concentration in your blood is controlled very rigorously. And the parathyroid glands, their job is initiating a response to calcium level going too low. So if calcium level goes too low, we want to bring it back up. And it is the parathyroid glands that are incredibly important in initiating this response. Okay, so the function of the parathyroid glands is that they continuously measure the blood calcium level, and if the blood calcium level goes too low, i.e. you become hypocalcaemic, then they are going to start releasing a hormone, and that hormone is known as parathyroid hormone. So I'll start by writing out parathyroid hormone, and throughout the video what we're going to be doing is abbreviating parathyroid hormone down to PTH. So this will probably be the only time in the entire video that I actually write out parathyroid hormone in full. From now on I'll just be abbreviating it down to PTH. Okay, so the parathyroid glands then, they synthesize, store, and then secrete parathyroid hormone, and they secrete it in response to blood calcium level going too low. And parathyroid hormone, along with vitamin D, and we'll understand vitamin D later on, are going to work to bring blood calcium level back up. So that's the role of the parathyroid glands, responding to too low blood calcium level and bringing blood calcium level back up. That's the broad overview. Okay, so now let's have a look at the histological structure of a parathyroid gland. So now we've done the gross anatomy, now let's actually zoom in on a parathyroid gland. But before I just do that, let me give you the normal diameter of parathyroid glands. So people usually quote the diameter of a parathyroid gland as 4 millimeters, okay, which is a distance of about that long. Okay, that might be closer to 5 millimeters, what I've drawn there, but it's about that sort of size. So very, very small little glands. Okay, and you have 4 of these. Okay, so now what I want to do is zoom in on a parathyroid gland and have a look at its actual cellular structure, its histology. And this is quite nice because it is so simple. Okay, so here then is my parathyroid gland, now zoomed in on hugely. Okay, so the outer portion then of the parathyroid gland, it's surrounded by a capsule. So I'll firstly colour in the capsule here in blue. So the outer peripheral aspect of the parathyroid gland is coloured in a capsule, which we will show in blue here. So this is the capsule of the parathyroid gland in blue here. Okay, now let's actually draw the cells of the gland inside. So there are only 2 different types of cell that you're majorly going to find in the parathyroid gland, and the main one, the one that actually synthesizes the parathyroid hormone, and the cell type that is most prevalent inside your parathyroid glands, are known as chief cells. So I'll draw a few of these here. So here's one, here's another one, here's another one, and you're going to have lots and lots of these chief cells. I'm not going to fill the entire picture with them because it will take too long, but you could, if you liked, continue this picture on and actually fill in the entire parathyroid gland here with these chief cells. Okay, and you wouldn't be too far off what the parathyroid gland actually looks like. So these cells here are known as the chief cells of the parathyroid gland, and their role is in synthesizing, storing, and then in response to hypocalcaemia, secreting parathyroid hormone, or PTH. So these are the chief cells of the parathyroid gland. Now there is another cell type in the parathyroid gland which you should be aware of but isn't going to play any part in our story here. Okay, and these are known as the Oxyfuel cells, and they're going to be much larger than the chief cells. So here is a much larger cell, and they'll just be dotted around the place. So amongst the chief cells, you're going to have these much larger cells known as Oxyfuel cells. I'm sorry if I just called them chief cells, they're not chief cells. This other type of cell is known as the Oxyfuel cell. So this much larger cell here is called an Oxyfuel cell. So amongst all of the chief cells of the parathyroid gland, dotted around the place, you're going to have these Oxyfuel cells, which are much larger. Okay, so to summarize, this is the histological structure of parathyroid gland. You have a capsule around the edge, and most of the cells inside are these little chief cells whose job it is to synthesize, store, and then secrete parathyroid hormone. Dotted around the place, you also have these Oxyfuel cells, which are much, much larger in size than the chief cells. And by the way, these Oxyfuel cells have no known function. Okay, so we don't know yet what their actual function is. Maybe they don't even have a function, maybe they are evolutionarily redundant now. Okay, but they are there regardless, so if you actually do look at a histological slide of a parathyroid gland ever, be aware that you won't just see the chief cells, you will see occasionally these larger cells known as oxyfuel cells, which at the present we don't know whether or not they have a function. No known function is there for them. Okay, right, so that's the histological structure of a parathyroid gland. So now what I want to talk about is blood calcium level, because that's where this story begins. Okay, the role of these chief cells in the parathyroid gland are to synthesize, store, and then secrete parathyroid hormone, and they secrete it when blood calcium level goes too low. So we need to know something about blood calcium level. Okay, so what I want to talk about then is blood calcium. So calcium, firstly, let's start off with calcium. Calcium is, of course, an atom, but usually it loses its outer 2 electrons and becomes the ion. Okay, so the form we are used to seeing it in is calcium 2+, where it has lost its 2 outer shell electrons and is now a divalent cation. Okay, and there's going to be lots of these calcium cations, or just calcium ions, in the blood. Now, the calcium ions will be in 3 major different forms, and we need to be aware of these 3 major different forms. So the 3 major different forms that calcium ions can exist in within the blood are they can exist as the free ion. Okay, so this is just the free calcium ion, the divalent cation, dissolved in water, so it will be surrounded by water molecules, the partially negatively charged oxygen atoms of water molecules will of course be surrounding them. Okay, that's one of the major forms that calcium ions can exist in within the blood. So in the blood you're going to have calcium ions. A lot of them are going to be in the free ion form. However, not all of them. Okay, so there are 2 further forms that calcium ions can exist in within the blood. The second form is that they can be bound to plasma proteins, in particular albumin. Okay, so how does this work? Well, plasma proteins are of course polypeptides. They're made up of loads and loads of amino acids. Now, some of the amino acids will have negatively charged R groups. So for instance, the acidic residues, glutamic acid and aspartic acid, they have carboxylic acid groups in their R groups. And those carboxylic acid groups can end up donating their protons away into free solution, and therefore will end up with a negative charge. They'll become the conjugate base known as glutamate and aspartate respectively, and then those negatively charged amino acid residues can then bind to calcium ions. Okay, so what can actually happen is calcium ions can end up associated with negatively charged amino acid residues on plasma proteins. And one of the plasma proteins that is particularly good for transporting calcium ions is the plasma protein albumin. I mean, albumin transports all sorts of things around the body, such as free fatty acids, for instance. But one of the things that it can transport in addition is calcium. Okay, right, so calcium can be transported around the body then by binding to plasma proteins. Okay, so the final form then that the calcium ions can exist in within the blood is that they can be bound to much smaller negatively charged ions. So here we had calcium being bound to negatively charged residues of these massive great proteins. The other form that calcium ions can actually exist in the blood is being bound to much smaller negatively charged ions, and one of the principal ones that they can bind to is phosphate ions. Okay, so you also have phosphate ions within the blood, and calcium ions can bind to phosphate ions because they have a negative charge. Now, phosphate ions for short are often abbreviated down to P with a subscript I. The I here is for inorganic. Okay, so inorganic phosphate ions, because they don't have any they don't have any carbon atoms in their structure. Okay, now, I would just like to take a little bit of time to go through phosphate ions, because this is a point of some confusion, because there are 3 different things that you could actually refer to as being a phosphate ion. And I want to go through these three different things because it will become important later on, and it's something that a lot of people don't understand particularly well. So, phosphate ions. There are three different phosphate ions, and they all come from the acid phosphoric acid. They are all conjugate bases of the molecule phosphoric acid. So we'll begin by looking at phosphoric acid then. So phosphoric acid, its chemical formula is H3PO4. Okay, and its actual chemical structure has the phosphorus atom, the P here, right at the centre, and it has the 4 oxygen atoms surrounding the phosphorus atom. So one of them is going to have a double bond to the phosphorus atom, and the other 3 are all going to have single bonds. And then the 3 oxygens here, of course, they need another bond because they need 2 bonds overall, and they've only got 1 to the phosphorus atom, so they make it up with a hydrogen atom. Okay, like so. So there is the chemical structure for phosphoric acid. And phosphoric acid, as I say, is going to be the thing which gives rise to all 3 phosphate ions. So phosphate ions are going to be conjugate base molecules of phosphoric acid. Now, phosphoric acid can actually donate away 3 protons into solution. So remember, the definition of an acid is a molecule that's capable of donating a proton away into solution. Phosphoric acid is fantastic at this because it has 3 different protons that it's capable of donating away. So these at the moment are covalent bonds between the oxygen atom and the hydrogen atom. Okay, so if I just draw this out, we'll have the oxygen here and then the hydrogen here. So this bond will consist of a shared pair of electrons, one coming from the oxygen and one coming from the hydrogen. But what can happen is the hydrogen nucleus, which usually just consists of a proton, can abandon the bond here, leaving its electron with the oxygen, giving the oxygen a negative charge, and it will then go off, and that proton will now have been donated into the solution. Okay, and in the case of phosphoric acid, this can happen for each one of these alcohol groups here. So it's actually capable of donating away 3 protons into solution. And depending on how many you have actually donated away into solution, that will determine which of the phosphate ions you're actually going to become. So, what you can do then is donate 1 proton away, and what you'll end up with is this structure here. So let's say you've donated this one away. Of course, this is a 2-dimensional structure, so it makes it look as though these are different, but of course they are all equivalent. If you think about the actual 3D structure of this, you've got the phosphorus atom double bound to the oxygen, and then around it, splayed off, you've got the 3 alcohol groups, and they're all equivalent, utterly equivalent. So don't be fooled into thinking that this one's somehow different from this one. That's just because we've done the 2-dimensional picture. Okay, so here is a negatively charged oxygen here, then we've got 2 alcohol groups which still have their protons here. Okay, and of course the formula for this would be H2, because we've lost one of the protons, and now it would be PO4, and we'd now have a negative charge, so it's H2PO4 minus. Okay, so that is considered a phosphate ion now. Strictly speaking, what this should be called is dihydrogen phosphate. So if you're being very strict, you should call this dihydrogen phosphate rather than just calling it a phosphate ion. However, in biology, we often just refer to this as one of the phosphate ions. Okay, so strictly speaking, this is called dihydrogen phosphate. However, this is under this umbrella category of phosphate ions as far as biologists are concerned. Next, of course, we can go to the next one along where we've lost 2 protons. Okay, so let me now draw this out. So here's the phosphorus atom, double bound to the oxygen, and now we're going to have 2 oxygens that have lost their protons. So we're going to have 2 oxygens with negative charges here, and then we'll have only 1 oxygen which has still got its proton, which is therefore still in the form of the alcohol group here. The chemical formula for this would be HPO4 2-, like so, and the name for this, the strict name for this, would be hydrogen phosphate. Although again, we will just refer to this as one of the phosphate ions as a phosphate ion. Okay, so this is strictly speaking hydrogen phosphate ions. Okay, so I'll underline this one here in red. And then, of course, you can go one step further. You can now donate away the proton from this final oxygen atom here to end up with 3 negatively charged oxygen atoms now, and that then is the final true phosphate ion. So if I draw this here, we'll have the phosphorus atom, double bound to an oxygen atom, and then the three oxygens have now all got negative charges like so, and this will be written, the chemical formula for this is PO4 3-, and this is truly what you would call the phosphate ion. However, we often call all three of these phosphate ions, all three of these different levels of the conjugate base of phosphoric acid, we often refer to them as phosphate ions. And all three of them are capable of binding to calcium ions because they all have negative charge, which can associate with the positive charge of a calcium ion. Okay, so dihydrogen phosphate, hydrogen phosphate, and the true phosphate ion, these will all be written Pi, like so, as far as biology is concerned. So when people write Pi, they mean any of these three, not necessarily this one. And in fact, in the normal pH of blood, you have very little of this one. It's mainly these two that are actually in existence. So in the blood we have phosphate ions, and of course the equilibrium for these will all be in dynamic equilibrium with one another. The equilibrium is going to be determined by the pH. If you've got a very high pH, then that's very basic, very low concentration of protons, then all of them are going to end up going into this form here, because they're all going to end up donating their protons away into the solution, and they're not likely to get them back again because the proton concentration is so low. Whereas if you've got a very low pH, very acidic pH, very high proton concentration, then they're mainly going to exist in this form, the phosphoric acid form, because as soon as they donate their protons away, because the proton concentration in the solution is so high, they'll just get them coming back onto them again. Okay, so the balance between how many of each of these forms you actually have here is determined by the pH of the solution. Now in the case of blood, pH is controlled hugely. The pH of blood is usually between 7.35 and 7.45, so neutral but slightly alkaline, to the alkaline side here, okay, above 7. And at this pH, the main form that these molecules are going to exist in is in the middle two forms. So you're mainly going to have dihydrogen phosphate ions and hydrogen phosphate ions in the blood. You're going to have very few actual true phosphate ions, and you're going to have very few phosphoric acid molecules. Most of these molecules are going to exist in these middle two forms here. Okay, so when we say phosphate ions, then we are referring to any one of these three, not necessarily the true phosphate ion, because the true phosphate ion is very rare within the blood. Okay, so the other form, the third and final form that calcium can then exist in within the blood, is bound to these phosphate ions, any of these three, which we'll now just denote as Pi here, and it can do that because they have a negative charge and the calcium has a positive charge. Okay, and that complex of calcium with the phosphate ion can then move around in the blood. Okay, so those are the three forms in which calcium can exist within the blood. Now this is important so that you understand the difference between total blood calcium level and the actual free ion calcium concentration. Okay, so when we talk about total blood calcium concentration, or just total calcium concentration, like so, that means the concentration of calcium ions in all three forms. And when people in a clinical setting talk about taking plasma calcium levels, they mean total calcium concentration. So if you've got a clinical measurement of someone's calcium concentration in their blood and it just comes out, you know, the title of it is plasma calcium concentration, okay, they mean the total calcium concentration, i.e. the calcium concentration in all three of these forms, and that usually is between 2.2 and 2.6 millimolar. Okay, so 2.2 to 2.6 millimoles per litre. Okay, so that's the normal range for total blood calcium concentration, i.e. calcium in any one of the three forms. However, we also talk about another measure, which is the actual free ion calcium concentration. Now this one is very difficult to actually measure in a clinical situation. So usually in a clinical situation you're talking about total calcium concentration, not free ion calcium concentration. However, the concept of free ion calcium concentration is important because it's that concentration that the parathyroid gland chief cells are actually going to be measuring. They won't be measuring the total calcium concentration, they'll be measuring the free calcium concentration. And it's the free calcium concentration that is absolutely essential for you to keep normal, because remember, that's the one that's going to be affecting ion conductance across cells, not the cell membranes, which is of course extremely important for determining cell behaviour all over the body. And I should have probably given a speech about this earlier. Why is calcium so important to keep the same? Why is it so important to keep plasma calcium concentration the same? Well, it's because calcium is used for intracellular signaling processes all over the body. We have voltage-gated calcium channels which are important in allowing calcium into the cytoplasm of cells to create signals which change the behaviour of those cells all over the body. Okay, so we need to keep the extracellular calcium concentration, which is the free ion concentration. We don't care about calcium that's in these forms. We want to keep the free ion calcium concentration the same, okay, so that we don't distort these intracellular signaling processes. Okay, so free ion calcium concentration is actually the really physiologically important one. It's this that we want to maintain. We don't really care about maintaining this one, but this is the one that we measure clinically, so it's important for you to be aware of the difference between these two. So now let's talk about what is the normal free ion calcium concentration. Well, the normal range for this is between 1.3 and 1.5 millimolar. Okay, right. So it's really important that you do understand the difference between those two, so I will just recount it again. So free ion calcium concentration in the blood, that is obviously in equilibrium with the free ion concentration in the extracellular fluid, so they're the same. Okay, free ion concentration in the extracellular fluid of calcium is extremely important to keep the same because of intracellular signaling processes which are triggered by the entry of calcium into cells through calcium ion channels. Okay, remember, calcium concentration inside cells is kept ridiculously low at around 100 nanomolar. Okay, and one of the key ways that we can change behaviour in cells is bringing calcium into the cytoplasm of cells, and it has a huge number of different effects. So calcium signaling inside cells is extremely important for cellular behaviour, for controlling cellular behaviour. Okay, so if we're going to have our signaling pathways inside cells working properly, we need to keep extracellular free calcium ion concentration the same, and that involves keeping blood calcium concentration in the free ion form the same. So this is really important to keep the same. However, when we actually do clinical tests, it's very difficult to actually measure that. Instead, we end up measuring total calcium concentration, i.e. not just the concentration of the free calcium ions, but also the concentration that we get from calcium that was bound to plasma proteins such as albumin in the blood, and also calcium that we got because it was bound to phosphate ions within the blood. So total calcium concentration is therefore higher than free calcium concentration, and that usually is between 2.2 and 2.6 millimolar. Okay, so I hope you now understand those two concepts. And what we'll do now is we'll have a break, and in the next video what we'll do is move on to the synthesis and storage pathways for parathyroid hormone, and then we'll actually start looking at the pathway, the story, which is how do parathyroid glands respond to hypocalcaemia.